everyone. I'm happy to be the first presentation after your first coffee in the morning. So I hope to make it like as entertaining as possible. My name is Beatriz Fraga. I work for IES. We are a consultancy, a software company in digital twins. But this presentation is actually about optimizing operational energy performance through augmented intelligence dashboards. So there is a big process behind this. Like we have development, we have the simulations. I'll focus on the end user experience and the UX design for these operational energy performance dashboards that it should help the user to improve performance and reduce energy. So I'll give you an introduction with a bit of a context, some goals, and then how is our process, the methodology. Then I will show you the final prototype. I call it prototype because with these designs, I think they keep evolving with new end users' inputs, the development and the backend keep changing, to be honest. So that's the challenge of these dashboards, that it's a continuous improvement till the final delivery. But I'll show you the prototype, some conclusions and question and answers at the end. So all of us know like the ambitions we have at European level for 2030. And part of it is like they have this European Strategic Technology Plan, where it's not only about we need to reduce final energy consumption and primary energy, but also to include ICT systems, also to use the advancements of AI and all these technologies. So we have to use them to actually make the user capable to make the most of these technologies. So this task was part of the Outland project, where the main objective of Outland project is provide real-time suggestions to the user, which are building occupants. This is focused on domestic buildings and small size medium buildings. So where they can actually improve the performance with actions. So something to remark is like augmented intelligence is not something like to make the system completely autonomous, but to make the user part of the process and make actionable, and you provide actionable actions to them so they can interact. It's not fully autonomous system, but it's like a mix of both. We have the system and we have the user, which is quite nice. We are not going to be replaced by robots with this. And there's some demand. That's where the demand response actions come into place in Outland. So the goal of this task was to understand the user needs, and collect the feedback and talk to them. There was a lot of communication in this process, because the second goal was to create something that they encourage them to change the behavior, because no matter how smart or how clever is an engine or a platform, if the user is not going to do anything with this. So we need to encourage them and make them part of the process from the beginning. And at the end, test and optimize. That was the goals. So the process is human-centric design. Like the user is the core of the whole process. And I would say is divided in 3 blocks. So first you have this strategic alignment. Then you have research and analysis, that is more together. And at the end, you have the design and test. I just put a description here of a common way to describe human-centric design. This is like a problem-solving technique that puts people in the center. So you actually meet the user needs, because I'm sure all of us have seen products that at the end don't meet what the user expected, and that's actually a shame, because you probably put a lot of effort in that product. So what are the questions behind this process? The common way, why, what, and how. What does motivate the user? What are the drivers? Well, why? Like the user should have said, why does motivate the user? Then what are the features that they expect, and how it's going to look like. That's where the design come into place and the style of the final platform. So the first step, the strategic alignment. That's where we decide what the problem is. So that's where we create a problem statement. We meet all together there that are part of the process, like from the innovators, from the developers, and define what's the problem, the goal, and also the personas that we are talking about. The solution, so not the solution, but the result, the problem statement was that actually the building owners and the persons responsible for managing the energy, they find a gap between the energy price and the consumption. They didn't know how to match those two factors. And so if they understand that, then they will be able to actually behave different to make a change in the energy consumption. So currently, as I said here, there is no way for users to take actions, which actions to take to change the energy consumption. So that was a problem. We need a dashboard, well, not a dashboard, but a full platform that helps users to decide what to do to take to change the consumption. So from that stage, we also defined the goal. The goal was actually create these augmented intelligence dashboards where you can visualize trends in energy. You can also provide feedback and recommendations to the user and execute like some demand response actions. We're trying to make the automated control of it. That's in progress at the moment. And identify the targets. And then after that, when we have this problem resolved, defined, and everyone agrees, we just start with the research and analysis. Here there's like a lot of workshops and user interviews and desk studies on behavioral and psychologist theories about how people accept certain recommendations. And this is going to give that photo persona that is going to fit the final development. That takes a lot of time, because if you want to do it well, you have to use a lot of communication, and communication takes time. So after that, that's what we had in our Amsterdam project. That's the building, the users that we had. So, and each of them are different, and each of them have different needs and different drivers and interests. So there's a big difference between a business owner or a student, right? So we found out most business owners or managers, they're more focused, as expected. They were more interested in cutting costs, reducing the energy, or knowing when is actually this high peak and how can I change that peak. And then you have other ones, like the students, that they don't even have attention, they don't pay the bills, so they were more keen on comfort than maybe a building manager. There was a challenge. We found six of them, and we tried to do a prototype now that fits all of them, but they would have probably split in two. We're going to have one that is more oriented to industry or facility managers, and one that is going to be more for domestic. The one I'm showing is the general one. So the key takeaways of this research was, something that we already know. The students were financially motivated. Some of them, although there was an awareness of the environment and all, people at the end were more worried about their pockets. That happens. Then we have the lack of details. Those are the key takeaways of the whole research process. So they find it difficult not to be able to track appliances level. And that's something that we managed to include part of the dashboard. Then there were limited knowledge of how to save energy, and then comfort and convenience dictate behaviors. Some of them assume and actually accepted that they're not gonna compromise comfort for a solution that actually gonna save energy. Some of them that was the way of seeing it. So, and then at the end of it, we have the design. And that's where we sit down, we do sprint designs, we take all the insights for the key, for the ones I just showed you. And in this design workshop, to develop the digital prototype, that's all disciplines are sit together. And that's a challenge because you have UX design that is very focused on the user. Then you have the backend guys that actually focus on, we cannot do that. We cannot show recommendations based on that. We only can share like for the next day. We cannot show recommendations maybe for a week. And then you have the users. So having all this together is a process that they haven't been involved before. Maybe it was more involved in the backend part of it. It is challenging and it's really difficult to have all together and agree. If you want to have a final product that actually meets the user, so the user needs. So I just put here some part of the online design sprint that we've done in this activity. So it's very common in agile development in projects, and encourage collaboration because, as I said, like we have to sit together and talk. It makes possible to explore ideas and you obtain data for real users from the beginning. I just put pictures here of the online design sprint where each design team member produces a prototype. Then the prototype is discussed. Then they decide which one is right. And at the end of the day, the stakeholders vote like which one actually address what they expected to address. And some of the solutions were, all of them were validated. Some of them were, okay, we cannot add that, right? Like that's also the challenge of having users involved. Like they want to cover everything in the needs, and that's not easy. The second slide is just to show you a bit of final concepts that ended up there, and that's the prototype. That's the final prototype of, well, as I said, I think that needs continuous input and it's gonna keep improving. So that's the home page. So you will open your dashboard. You will see common operational like indoor conditions and temperature, right? So in the first overview, the displays you have here. So you will have the display of your real-time energy consumption and also the breakdown of the appliances, which is noisy in the back-end side of it because sometimes you have a smart plug, sometimes you don't have it, and that's a difficult one. Then you can see your energy savings in compared to some goals that you can set, and you can see the appliances usage, then the sensors for humidity, temperature. And on the right-hand side, you can see the recommendations or where to use it. So when to use your appliances based on energy prices and the pattern of your own behavior. I just put 3 tabs so we can have an idea was there. And then for the appliances usage, the user here is able to see where is the peak of usage, the lower and the medium. So because some you use your appliances, but you're not aware of how often you use it, or do I put the dishwasher all the time at the same time? So here you have a clear picture. I think it's very visual, and the user have a clear picture of when do you use your appliances the most. And that's a part of the goals I was saying. You can set up your goals, so then at the end you can compare how are you against your goals. Goals sometimes are just the benchmark, right? Like the previous bills maybe, or you just can check with the past. Some people are very clear, but usually at domestic level, they are more oriented with previous bills. And that's a bit all. So I just put 3 points and conclusions. That is, we discovered information communicated was relevant. So we have this continuous communication with the users. We do believe like the energy consumption final aspect will potentially change the drive. Like if you actually show that you're going to save that amount of money, that's something users like. I would like to. The product, and that's what they said, this product will continue to be monitored and we still need to gather conditions in the platform to align with the engine in the whole project, like with people. Some people are doing different tools for demand response, for instance, so we need to make sure that aligns and we can show there. And then the last sentence, like end users are not taken only as a customer, but also co-designers of the solution. So I think that's the key point of the UX design team in IES that put a lot of effort here. And that's me. Thank you. You have here like Autodan project you can follow, LinkedIn or in the website. If you have any questions, feel free.
I would like to ask if this tool at the end of the project is not ended.
No, there's a year and a half.
The idea is to develop a commercial tool that can be put in the market.
Yeah, hopefully, because it is actually it's gonna be. We have tablets, so and it's being tested already in tablets. So hopefully we can use it as service. So we're actually.
Who is the company who developed the software?
Yes, ourselves. Yes, ourselves. Yeah, because there are a lot of most of the services we show, like the appliances, we have developed the digital model behind that. Then the digital twin is all going to show and use for the comparison with your goals. And some other partners will show also demand response services, but they're going to send the data. So at the moment, we are developing the.
Okay. So if everything goes fine and the tools are effective, the idea is to put it in the market.
Yes. That could be definitely feasible.
Otherwise, what was the? I mean, I understand that the developing know-how and putting
Yes.
But if this doesn't go up to the market at the end.
No, it definitely has the potential and has the infrastructure to do it, because everything is being developed behind this. It's not only an idea, and as I said, during the whole process of designing that, I focus on the end user experience, but to present the UX design part, but behind that there's like a lot of work to make it work. So it's not only the design, definitely. And now, like, we need to do, like, we're working on the magic to make the models to talk to the dashboards and the users being able to use it. So yeah, would you buy it? We can talk later. Thanks for the questions. Well, that's me. Sorry. Yes.
I think that idea is really good because the only thing that the user feel compromised is that they know what to do. And we need to teach the user to improve the behavior. And my question is, do you have a simulation machine to advise also the user, or the platform only work with the data that you collect from the...
We have both. Mm-hmm. So the idea is to combine both. So what is that? The recommendations that are at building level, they are coming from the digital twin, or that we use our software for it, and and that's under development. We have the baseline, but we haven't got the data yet. So what is at building level is going to be about comfort, which is building level, and comfort is coming from the digital twin. And when it comes so the services for the appliances is a machine learning model. So it's more data. So they have, the product innovation team have developed a platform, an algorithm to actually identify the patterns where you are more, where you use the more energy, the most your appliance. Okay, so they are behind that. So appliance level, we have data machine learning techniques, and then at building level, it is the digital twin.
And there are also advice regarding how to use the energy system and how to operate the buildings. For example, we need to open the window now, or is recommended to open the window now? Is recommended to close the window?
Well, that's not part of this solution, because Autodan is more focused on the operational side. So it was very focused on the appliances and the energy consumption per se. But that's definitely, when it comes to comfort and recommendations for comfort, like if you open the window, that would affect this way or the other way, it's something that you could implement. It was not part of the solution, but with the digital twin and the algorithms that we are making, it's something like you can implement. And we work in other projects like that, I believe.
Nice. Thank you.
That's good. Sorted.
So did you receive this presentation?
Yes, we fixed so we can follow the same order.
Okay.
That's not the slides for today.
No. But
I just sent it to the account.
It's not this.
It's not this.
so this is an older version.
Yeah, that's my presentation for tomorrow.
Okay, sorry. Then we need to. Yes. I'm sorry.
Maybe I sent the wrong.
Let's end the show. You want 9% and then
Yes, because I need to ask again.
this one or no?
No.
No?
You have to.
Okay. Okay. Well, good morning, everyone. My name is Facundo Bre. Currently, I'm working as Marie Curie Individual Fellow at TU Darmstadt in Germany. And today, I'm going to talk about a simulation-based platform to design high-performance engines that use phase change materials. So, to start, let's talk about phase change material, or PCMs. As probably you know, these materials are substances that can absorb and release large amount of heat during the phase transition. For example, in this picture, we can see the main difference between a material without phase transition and a material with phase change. And the main difference is that the PCM of the phase change material can accumulate and release large amount of heat without increasing the temperature of the material and the surrounding. So this phenomenon we can employ in buildings for heating and cooling application, but this is the ideal theory. In practice, we have the challenge to convert or transfer this ideal theory to real-world applications. And despite the plenty of contribution in this field, we see lack of a full understanding what is the best way to design PCM in buildings. In this context, the Zero Building project aims to develop a simulation-based platform to evaluate and optimize PCM in buildings. And in this presentation, I will show some of the results we got during the project. My presentation is quite technical, sorry. Regarding the modeling of PCM, and there are several approaches to do that. For example, in energy class, the thermal capacity of the PCM is calculated using this equation that is a numerical derivative, where above we have the difference between the current and previous enthalpy, and below the difference between the current and previous temperature. And I recommend to use that model. That is the single curve model of energy class, and the main input is the enthalpy curve of the material as function of the temperature. There are also models to predict a particular phenomenon of PCM called hysteresis. And hysteresis introduces a temperature delay between the melting and solidification complicating even more the behavior of PCM and the modeling. And Energy Plus also has a model to represent this phenomenon, but in one of our works, we demonstrate that that model is not energy conservative. That means that the model, because of the approach employed, generate a virtual or numerical energy, and we can predict large heating and cooling load saving, but actually don't exist. And I will not describe this work, but anyway, this is a problem of the whole state of the art, not only for Energy Plus, and in my opinion is a big challenge from the numerical point of view. What is important about the design of PCM in buildings? We have several PCM design parameters, such as melting temperature, location and modes, thermal conductivity, thermal capacity. But usually researchers focus in the three first one, and in particular the melting temperature is considered as the main design parameter. For example, if we take that commercial building and put PCM inside the building and optimize both heating and cooling load, we can obtain a parameter from like this, where in one extreme we have the best design to reduce the heating load, and in the other extreme we have the best design to reduce the cooling load. Then the optimal melting temperature will be mostly within the temperature range of control of our HVAC system. That is important because if we have a PCM with the melting temperature outside this range, and that PCM will never have a phase transition during the occupied hour. So that PCM will never work for us. And then the best design to reduce the heating, we have a melting temperature near to the set point for heating, and the best design to reduce the cooling, we have a melting temperature near to the set point for cooling. So, given this trade-off, we propose to use an optimized PCM with different melting temperature in buildings. And that is one of the applications of our platform. So in this small office, we incorporate 3 different PCM layers in the external wall, the internal walls, and ceilings. And we solve a multi-objective problem, optimization problem, to reduce the annual heating and cooling load. And the design variables are the melting temperature and the thickness of each PCM layer. So to evaluate this new approach, we selected climate representative locations according to the ASHRAE classification, and in particular in the region 6 of the World Meteorological Organization, that is called Europe. The ASHRAE classification has 9 main climate zones or climate regions, classified according to the heating and cooling degree days. So thanks to the detailed information that Drew Crowley and Linda Lowry provided us regarding the weather data they generate, we selected these representative locations that are the nearest location to the centroid of each climate zone. And in that picture, for example, we have the performance of our baseline models in each climate zone or climate region. Here we have some optimization results, and in particular for the zone 1, 2, 3, and 4. In the figures above, we have the optimization results in the space of the objective function. And we can see, for example, that in these 2 regions that are highly cooling dominated, the Pareto front collapsed in one point, and we have a unique solution. Regarding the melting temperature in these zones are slightly different between the PCM and near to the set point for cooling. Regarding the amount of PCM in these regions, the optimal results indicate that the amount of PCM in the internal partitions should be lower than the other ones. And in region 3 and 4, we already have Pareto fronts and different and specific melting temperature around the Pareto front. Where here we have the same result, but for the region 5, 6, 7, and 8. One observation is that the design space increase when we have both silhouettes and a good balance between both silhouettes. In this case, the optimal results for the amount of PCM were the maximum allowed, and the melting temperature again had a specific values and different melting temperature around the Pareto front, and we can derive a general conclusion. For example, this climate region, the PCM that is located in the external wall is always designed to reduce the cooling load. These are the summary of the annual load reductions for each climate zones. And separating total load, heating and cooling. And the first conclusion that we can see here is that the best performance of PCM is achieved in climate region that we have both silhouettes and a good balance between both silhouettes. For example, the region 5, 4, 6, and 7. Another conclusion is that in climate regions that are highly cooling dominated, the performance of PCM can be limited. That is because the PCM cannot properly release the heat accumulated during the day because the high temperature and the low temperature variation along the days. Here we also conclude another general conclusions. For example, in climate region that we have both loads, the optimal design of PCM is always designed to reduce the lower one. And that is because the effectiveness of PCM increase under this condition. For example, in heating dominated climate region, it's easier to reduce the cooling load, and that is because we have a large temperature variation and the PCM can properly release the heat accumulated during the day. On the other hand, in cooling dominated climate region, it's easier to reduce the heating load, and that is because we have enough extra heat to accumulate in our PCMs. So, during the project, despite the use of advanced building performance simulation and optimization, I feel that the real effectiveness of PCM is still complex to predict in building. So I decided to propose new indicators to estimate the effectiveness of PCM in buildings. And this is the indicator I propose. It's very simple. Calculate the effectiveness of the PCM as the ratio between the annual load reductions and the latent heat storage capacity installed in the building. So to try or to understand this new indicator, we propose a sensitivity analysis using the Morris method for this case study building, where we consider PCM design variables such as the thickness and melting temperature of two PCM layers located in the walls and the roof. But also we consider variables of design related to the building envelope, such as the level of insulation, the window to wall ratio, and the dimension of this external shading. These are the result of the sensitivity analysis. And for example, for heating application, we can see that the most relevant design parameter is the window to wall ratio. followed by the amount of PCM in the roof and in the walls. For cooling application, again, the most relevant parameter is the window-to-wall ratio. Here, the dimension of the thermal shading take relevance, that is because the sun position, and also the amount of PCM is relevant. And for the total load, the results are similar, but with different magnitudes and order. Again, the window-to-wall ratio is the most relevant parameters. The amount is important, and the dimension of the thermal shading. So there are several observations we can have here, but the main conclusion is that we demonstrate that design variables related to the building envelope, such as the window-to-wall ratio, can have impact, high impact in the effectiveness of the PCM compared with typical design variables employed, such as the melting temperature that is usually employed. That is a big conclusion we obtain here. So, some conclusions that I got during the project. Until now, the performance of PCM in building is complex, and the proper design requires the use of whole building performance simulation, and not only for a wall or for a roof, we need to use whole building performance simulation. And the melting temperature, amount, and location of the PCM should be carefully designed to maximize the performance. We also saw that the use of PCM with different melting temperature is recommended, especially in climate zones and case study with both heating and cooling load. Thanks to the new indicators, we demonstrate that building design variables such as the window-to-wall ratio have a significantly higher impact on the effectiveness of PCM than typical employed PCM design variables such as the melting temperature. We also saw that in some climates, the performance of passive PCM can be limited, so the design should be combined with other passive strategies and architectural variables. And in my opinion, at the early stage, is better. So there are several future works, but I want to mention these two. I'm working in the new version of the platform that incorporate all the acknowledgement during the project. I plan to publish in the special issue of this conference. And a simple web interface of the platform will be developed to give access to any building designer. So this is also important. The research data generated during the project is available in the Senado repository, in particular in the Zero Building community. So if you want to take a look and try, I would like to thank to the European Union for funding the Zero Building project through one of the Marie Curie individual fellows. That is all. Thank you. Yeah.
Well, congratulations for the proposal and that formula and all, because I understand the complexity behind that PCM, I suppose. So I wonder if the complexity of simulating that PCM at the end is a dynamic.
Yeah.
No, it's more like a dynamic process, so it's gradually release the heat or the cold, right?
Yeah, the heat that accumulates and releases.
Yeah, so I wonder if that could help with some maybe more like indoor dynamic simulation, like maybe with CFD or something like that. So you more than focusing on the wall. I don't know, just saying if that's something that could help with this type of materials. Because I heard that happens also when they insulate with air. When you put like an air insulation, apparently that's the same, like it's a complicated way to simulate that because the air also behaves like a gas inside. So
yes,
I was wondering, is there a way to measure that, like to measure how that heat releases internally.
Yes, and in this kind of simulation that are based on thermal-based zones,
Yeah.
and all the physics of the building are considered with a kind of simplifications. Of course, in real building, we have the effect of the air that is moving indoor,
Yeah.
and CFD can help to characterize that. But if you want to predict the performance of a building using CFD for long term, such as a typical meteorological year, is not practical because the high computational effort that you need to do that.
Okay.
So usually we employ building energy simulation at the thermal zones level that are quite accurate compared to other approach and can be addressed.
Yeah, definitely. Well, at IES, we do have these simulations based on heat transfer, like physics-based simulations. So I was wondering if maybe from the
Yeah.
But yeah, thank you for responding. You were about to forget.
I forgot.
I have two questions. Give me a minute. Give me that. Can I ask a question?
Yeah.
You are using PCMs in between walls, right?
Sorry.
You are holding PCM between walls.
In the walls, yeah.
Yes. How you are holding PCMs in place?
How?
Because when the phase changes, don't they?
Sorry, can you repeat?
How are you holding PCM in place?
Sorry.
There are modules.
Yeah. There are different approaches to incorporate. One approach is to use microencapsulated PCM that you put direct in the walls and can use in the plaster and so on. But there are also modules, as said, that we have a macroencapsulation using metal or another container, and you can put direct on the wall or on the roof, whatever you want. But PCM should be inside the building, in contact with the indoor air, because usually you can find researchers that want to put outside, but that is not good for the performance of PCMs.
There's one more question now. So, as I understand, by the very interesting study, as I understand, this was focused on the simulation of the optimization. Have you had a chance yet to test it in a practical environment?
No. This platform is in particular to design computational tools, and so building designer can employ. But in our laboratory, yes, they are developed a kind of foam insulation that they are increasing the thermal capacity using PCM, and they have 3 demo buildings in Sofia, Bulgaria, that they are testing. So let's see what happens.
And in Sofia, Bulgaria, are those climate types appropriate for this technology? Like how based on your melting temperature study, how do that climate perform?
Yes, depending on the climate, you need to design the PCM, the melting temperature, the amount of PCM, and so on. But you can employ for heating and for cooling application for both.
Okay, no, let's go because I guess it's getting late. So the presentation.
Yes, everything is ready.
Okay. So as you want, again, for my presentation. Yeah. We're going to have cuando presento el link, además de una foto de solo para que
no se,
Te digo yo cuando solo
no se bloquea.
No.
So you are going first. Is this the correct?
web counter.
No, it doesn't work for the
Okay.
pointer. I'm sorry. Sí.
Vale, entonces voy a usar el teclado este, ¿no?
Sí.
Okay. So hello, good morning. I will make an informal presentation. Perdona. No, te lo.
Sí, pero para que.
Ok. No, solo la slide del infinite que me interesa. Okay, I will present some results obtained in the frame of a European project called Infinite. I will focus on the effect and the impact of dynamic glazing of smart windows. So let's start quickly about the impact of glazed facade in a building envelope. I mean, it's known that the glazed facade is the weakest energy point of the envelope, so everybody knows that. But despite this, not many efforts have been put in the last 20 years in this direction. I mean, architects nowadays try to conciliate aesthetical issues with functional energy performance. You know, an example, it's not always easy because I mean the environmental condition affects the performance and the comfort if you have a glazed facade. So the impact of having a well-designed insulating glazing system in terms of European building stocks is huge. There are some study made. One of the more recent study made by TNO demonstrated more than 50% of the energy consumed in Europe for residential buildings can be saved if the windows could be replaced with better windows, let's say, with higher insulation properties. And of course, the reduction in terms of CO2 consumption is huge. So it's evident that improving the quality and efficiency of this is a good example here. We have, I guess, single layer glass of the 40 years ago, more or less. So this is a absolutely huge topic. What's the trend in terms of the R&D and market perspective? The trend is going from 97 windows with very high thermal transmittance to lower thermal transmittance, high insulating glazing systems. And the trend is to go toward net energy systems, dynamic glazing systems that can intelligently adapt to the different environmental conditions. Just a number. I don't want to spend so much time in introduction, but this is a number that is very, very useful. All the designers, building designers, focus on the thermal insulation and to guarantee good quality indoor. So typically, the issue is preserve the heat generated indoor, for instance, in winter, to avoid thermal leakage, no? But if you consider the energy that you want to save in a winter condition with a typically wall of 1.1 watt per square meter for Kelvin, in winter you have a loss of about, let's say, 30 watts if you want to avoid the loss of radiation due to leakage of heat. In summer, in the same building, same condition, if you just consider a glazing facade with a 60% of solar factor, it's the classical number, the amount of solar radiation, the amount of energy produced by sun that enter the building is about 460 watts. So it's, let's say, 20 times higher. And this is an imbalance in the design of the building envelope. Too many efforts in having super insulating walls and not enough effort to have very efficient glazing facades. So, what's our solution, our proposal? The technology we are working on consists in having a smart, intelligent glass facades that can change their thermal properties. In particular, they can adapt to the near-infrared radiation, so letting the thermal radiation enter the building or not, depending on the condition. For instance, in winter, you can have solar radiation reducing the heating loads, and in summer, you want avoid heating up the environment. The same principle of PCM basically is the same principle. Actually, some PCM materials are used as smart windows in some cases. This is why it's very important, because if you look at the solar spectrum, 50% of the energy transported by solar rays is in the near-infrared radiation. So 50% is thermal radiation. And we want to focus on this part. We patented a solution that allows to implement what we refer as a dual-band electrochromic systems. So electrochromic glazing are systems that change the color of the optical features. We improved the existing functionalities by using engineered nanomaterials. So I don't go into these technical issues because I'm sure that nobody is pretty interested. Just a very quick spot. Here you have a glass prototype under the solar simulator. So here you have sunlight. This is the say intelligent glass. When the glass is off, the light passes through the glass and the black surface behind gets hot. This is imagining with the thermocamera. When you gradually activate the glass, this is the control filter, let's say modulate the infrared radiation. The upper surface of the glass is getting hot, and the temperature behind is getting lower. So at the end, when you totally filter the solar radiation, the black surface behind is getting at the same color of the environment. So you are not heating up the environment behind. So now, please, I can ask you a couple of pictures because I will go in the platform. So we are implementing this solution in the field, in the frame of Infinite project, which is a project funded by Horizon 2020, focused on residential buildings. And the project is aiming at developing, let's say, 7 building kits that can be installed in a modular way on the building facade. In particular, I'm focusing on the smart window kit. In collaboration with VZ and Rubner, that are 2 companies involved in the development, we are integrating this solution into smart dynamic glazing that can easily install it and, use it as retrofitting solution. The idea is not to install new buildings, but to renovate the existing solution. So, few words about the fabrication. I mean, we are fabricating these modules, this technology from nano engineered materials. We are using screen printing techniques. We fabricate these modules and integrate it in an IGU. These are a couple of pictures of the prototype. We started a few years ago with the lab scale research, a small lab. At small sites, and then we are putting effort in scaling up the technology. These are a couple of prototypes that have been fabricated in the Infinite during the Infinite project. And what's the target? Okay, data about technical characterization. I can skip this part. The idea is to integrate this technology, of course, with let's say sensor and Internet of Things platform. Because it doesn't make sense that you have a very, very advanced technology and you are not able to control. So the 2 things go together. Engineer the nanomaterials and efficient control platform. So VZ is one of the partners of the project. They developed an intelligent control system that embeds solar cell and sensors. It's integrated in the IGU spaces, so between the 2 glass of the window. And the data of the window are transmitted, are interfaced with say what is referred as BMS, so integrated in the overall building control system. In this way, the window is, let's say, it's the driving force of the energy utilities of the building. So you know, if you need to heat up the environment during knowing the information that are coming from the windows. So it's just a schematic representation of the system in terms of sensor and the CPU. All the modules are connected with the LoRaWAN Wi-Fi platform. This is an example of the integration of the IGU into the building frame. So you have the smart windows, the local actuator, the control unit interfaced with sensors. And about the control. So you have a smart windows, you want to implement an intelligent smart control algorithm, so a control model. One of possible control model is an example of a good control model is reported here, where you have two variables, temperature and solar radiation. So typically you want to modulate the window functionality depending on the indoor temperature and the intensity of the light. This is an example. The main variable is the temperature. If temperature inside is lower than temperature comfort, you left the radiation entering. If you are getting hot, so you start to filter it out. No? So, and in this diagram, you see the colors that should represent the color of the window when you need to filter it out. So low temperature, low solar radiation, window transparent. Maximum temperature, maximum sun intensity, the window is getting dark. Okay. This can be made. The functionality can be extended due to the advances we made in this project by combining the two effects: the thermal radiation effect and the visible light effect. So when you only want to control the temperature features, you don't need to make the window dark. You just need to control the temperature because you want to daylight into the building. So this is the advantage of the technology we have developed. It's called plasmochromic technology, and this huge advance in terms of solar control capabilities. Because at the end of the day, the window should be integrated in the overall management of the building parameters. So to optimize the visual comfort, thermal comfort, and energy performance that are competitive variables, you need to take into account plenty of variabilities, of variables, like luminance, solar radiation, thermal loads, occupancy loads. And in this case, yes, that is super important having digital platforms and tools that support the data analysis. So the next step of the optimization of the performance of a building facade is integrating all the data and having an intelligent tool that allow the window to interact with the building occupant and with the user. So this is the final goal of every tool developed in the field of energy efficient buildings. So I guess it's all. Yeah. I tried to make an informal. Just to put the focus on what could be interesting for you. If you have any particular curiosity.
I was just wondering if you have explored or considered any sort of human behavior factors in these optimization and control algorithms?
Yeah. No. This is the point. This is the point. So when you make the window operating in an automatic mode, who is the priority? Which is the priority? Energy saving. Okay. Sometimes energy saving is not in accordance with comfort. So if today you want to optimize the energy performance of this building, maybe you start to get cold and say, no, increase the temperature. So comfort and the energy are sometimes not, should be conjugated, yeah. And this is why putting the user at the center of like the tool presented before, is the solution that integrates the technology.
Yeah, also that the user could potentially want to make changes of their own, and this would affect then the algorithm. And
in most of the demo cases.
Just window, like.
Yeah, in the demo cases, actually, what happens is that the people living in the buildings, after a few days, switch off the automatic control. They don't want the automatic control. They manually regulate because, of course, because the automatic control follow energy parameters, and any people is different in terms of. So, but this is a big issue. It's not only related to the window.
Exactly.
So the visual comfort aspects are not considered in the current control.
No, they should be considered, are considered, but when you know that then when you talk about comfort, the protocols available today as subjective call the predictive. For instance, for thermal comfort, there is a protocol called the predictive mean value of satisfaction. So air value of satisfaction is different from yours. It's something that is subjective.
Just a quick one. Thank you for the presentation. I want to ask you if you've made any economic analysis, like payback time.
Yeah, good question. I explicitly avoid to touch this topic, but this is a big question because our current cost of electrochromic glazing is quite high. So this prevents market penetration at the end. Yeah. Okay. So.
Si no se diera mucho que les
Yes.
Okay, so I cannot see it here.
Sorry, yes, it's frozen.
Okay, so my name is Dimitrios Ntimos. I'm with IES, colleagues with Beatriz and Amisa there. Currently project manager of R&D projects and coordinator of this project called iBECOME. And today I'd like to present you a case study we've done in our headquarters, which is an office building in Glasgow, where we're trying to improve the energy performance and also the comfort in the building using what we call a virtual building management system. So before I dive into the details of the case study, I'll try to do a quick introduction of IES and to the iBECOME project, and then I'll show you what this building is about and what we're trying to do to improve the energy performance and the comfort in the building, and then discuss a little bit what's next. So now IES is basically a software provider company, software developer, that we develop technology for building energy performance analysis. And our core software, which is called virtual environment, is basically used many years now by many companies worldwide, primarily in the AEC sector, architecture, engineering, construction. And as you see, there are more than 75,000 projects being analyzed per year. and more than 1 million buildings have been analyzed. In parallel, we do our own, we use the software on our own, doing analysis of buildings, and we invest quarter of our revenue into R&D. So now our vision is that we believe that every building of every city in the world can be decarbonized. And our aim is to create a built environment that is resource and energy efficient, eliminating global reliance on fossil fuels, while promoting comfort, health and well-being, and fair access to energy for every citizen in the world. So some facts about the iBECOME project. It's a project that started in June 2020, right after the pandemic started. We are 10 partners from 4 countries, UK, Ireland, France and Italy. Our project lasts 48 months and we're doing demonstration in 4 sites. And we're funded under this call, reducing energy consumption and carbon footprint by smart and sustainable use. So now what we want to achieve in iBECOME, to reduce the bills in a building or facility through energy savings and demand response, while improving comfort and well-being inside the building by leveraging IoT, data analytics, and the efficient control of the building, while also enabling additional services such as EV charging optimization. And looking at the targets we set in the project, we're trying to reduce energy use and energy bills by 15%, also comfort complaints by 20%, and air quality complaints by 10%. Improving the smart readiness of the building. Also trying to track, prevent and reduce equipment and operational faults by 20%. Improve the wellness, and also try to generate revenue from the energy savings, like to make like this as a business model. To we start with very low investment to trigger energy savings, and then using that, monetizing that energy savings, we invest further in more energy conservation measures. So basically, our software and our solution is primarily designed for 2 types of buildings: the ones that do not have a building management system, and other smaller buildings and other bigger buildings that have a management system but is inefficient. So on the left hand side you see the hardware that exists in the building, and if there's not, we propose a solution by Schneider Electric, which is a partner in the project, where through their automation server we connect, and through API connections we enable, as we see at the bottom, it's physics-based simulations, also dashboards and data analytics in the middle. And all of this is transparent and of course secure, and also working on the cloud. And through this system we are able to connect any device or any service. And some key devices that we need is this is a sensor, like an indoor temperature, humidity, motion, and CO2 and illuminants, and a thermostat. So if there is a smart thermostat, we can control it, like to adjust temperature of like a fan coil or of a thermostat, like a simple one. And in parallel, we do have a demand response service to respond to like if there's a demand response event. We have the intelligence to tell to the algorithm that no, you cannot participate in this event because there is not good thermal comfort in the building. So we need the equipment to work, for example. And our role of IES is on that side of the intelligent part of and data analysis and monitoring from the building. So just a quick glance like at the services of the project: energy comfort optimization, M&V, measurement verification, demand response, fault detection, diagnosis, predictive maintenance, and what-if scenarios. So using our model, we can even predict scenarios in the future. And some additional services that can be enabled is healthcare management. So we do demonstrate this as a management of a care home, where it's a home for the elderly people. It's a separate application and demonstration. EV charging optimization and car sharing so far. So and the infrastructure of the project gives this benefit of having someone that is that requires to use energy data, and they want to develop a service, they can use our APIs. And these ones, the highlighted ones, are the ones that we do in IES: energy optimization, M&V, and what-if scenarios. So through this project, basically to achieve the goals of this project in IES, we didn't have the technology yet. So what we developed through the project was a new calibration tool on the cloud. So for the physics energy model, to make it an accurate representation of the reality. That's how we call it. It's called a calibration process. We managed to do a two-way connection with Schneider's systems, the BMS of Schneider Electric. And then we advanced our simulation engine to be decoupled from the software package, put on the cloud, enabled co-simulation with other engines, and develop public APIs. And in parallel, we are developing machine learning models for the predicting comfort, for the heating cooling optimization, and the electricity flexibility optimization. So now looking at the case study, this is a picture of the outside of the Helix building. It's like a small to medium office, can accommodate up to like 180 people. It's mostly occupied by IES, apart from the one quarter of it, which is another company. And we've done a survey into the building. We looked at it as if we went there as auditors. And as we see, there are some pictures of the current status. The building already have some sensors installed, IoT sensors, that measure air temperature, CO2 illuminance, and the motion in key areas of the office. But there's no building management system, no BMS. The heating is on a weekly schedule, just like a normal office 9 to 5 operation. There's no local heating control. So, for example, there are some meeting rooms that follow the overall schedule of the building, even if they're occupied or unoccupied. So sometimes they're heated, but nobody is inside, and we have this kind of problem. So that's there's also a temperature difference between different zones in the building. We realized this winter that preheating is not enough in some very cold winter days. Yeah, I already explained this one. We had a physics energy model developed in our engine, but it was outdated and created to achieve like compliance with regulations. It usually happens when a building is designed or retrofitted. Someone like an engineer that applies for the getting some permit, they need to do an energy model and then they throw it somewhere. So this model can be revived, calibrated and used to optimize the energy in the operational phase of the building. There is certainly an air quality issue in meeting rooms. We measure a high concentration of CO2 in meeting rooms primarily, and there's no mechanical ventilation, just like opening windows when the air is stuffy. So now, what could be done in the building, what we have done to fix all these issues is we try to install devices from the market that already exist in the market. So as you see, we replace the thermostat with a Wi-Fi thermostat that's also portable. We also replace the valves of the radiators with some smart valves that can be remotely controlled as well, and have also some sensors inside that measure again the same like temperature and stuff. We install some Windows sensors. We manage to the heat meters and electricity meters of the building to put the data on the cloud and get like a continuous feed of like every 1 hour to get readings from heat meters and electricity meters. So without without the virtual BMS of iBECOME, the office manager of IES R&D would need to navigate to 4 or 5 apps every day to see one app for the heat meter, one app for the electricity meter, one app for the TRV, one like website or for the thermostat to make all this workload maybe daily, maybe once a week. Also to compare the energy bills before and after, receive complaints and all again go into the different websites, adjust heating, try to, it's basically a manual process, using spreadsheets to track and do reports and call technician when something fails. So it's all manual thing. And so now with iBECOME, we got into our software all the historical and the live data in one place. So the energy manager can log in only to this website and see all the live data, and even beyond the current time, since we do predictions. So this line here is now, and this one is prediction, using machine learning and physics, so that we manage to optimize the energy in the building. A single dashboard that shows this screenshot is showing just one room and the condition in a room, like temperature out of bounds, graphs with like comfort zones and color coded so that they easily can get the message. Alerts for data gaps and anomalies. So if we track a sensor, because the sensors are battery powered, if a sensor goes offline, we get an alert. Or if there is a problem, we get an alert. For example, we faced an issue where one of the TRVs started leaking, and we detected some humidity. So we, using machine learning, we now detect if there is a leak into the TRVs. We've made this like a LED to alert when there is a CO2 issue. It's above the comfort level because CO2 is not easy to detect, and we prompt like the users to open the windows. Again, we used our old energy model to recalibrate it. We're doing machine learning comfort predictions and fault detection. And now what the case study you see today is about the control of heating. So we do data-driven occupancy-based control in meeting rooms. That's one part to optimize the meeting rooms. Model-based comfort optimization in open office, and smart preheating for the next day based on the weather forecast. So this way we're trying to improve the energy use and primarily the comfort in the building. And we've done, we set up a demand response advisor which tracks the prediction of the CO2 intensity of the next day and the energy price, and gives an advice when to charge devices or when to plug in devices. And for example, there is a dehumidifier in the office. So we suggest or even control through smart plugs directly when there is lower CO2 emissions of the grid, of the electricity grid, we switch on the device. And energy savings calculations using MMV and what if scenarios. Something that we again can do with the IES virtual BMS. So now quickly I'll show you this comparison we've made. It's basically not deployed on the building, but we've done it last winter. Is a study using the energy model. Is a comparison between the current status of the heating, a proposed rule-based control, and an AI predictive control using artificial intelligence. So we estimated the energy savings, comfort improvements, and payback time when applying two different control strategies and comparing to the current status. This is a bit more technical. It shows the rule-based on the left-hand side, how it works. The artificial intelligence one on the right-hand side, which is using reinforcement learning, which is an algorithm that rewards itself when it achieves better results. So this was applied to efficiently control the heating in a building, in comparison with like a very simple rule base, like if the temperature is 22, reduce it to 18, like I said, fallback temperature. So the results in terms of the comfort, you can see in the arrows on the right hand side, is a comparison between the current status, rule-based, and AI control, artificial intelligence. And these are temperature zones like 18 to 20 degrees, 20, 22, and overheating here. So as you see, for example, with rule-based, we reduce overheating, with artificial intelligence even more. So it shows some good results already, like less overheating, more time in optimal comfort ranges using reinforcement learning. And in terms of energy performance, this on the left hand side is a comparison between three different open office zones. On the right hand side is overall for the building. So switching from the current status to a rule-based, we achieve 5 to 10% energy savings, and on top of that, even like a 5% more with reinforcement learning control. And this is with no significant investment. With the equipment we have and some small devices we installed. For example, the TRV for the radiators is like 90 euros. So it's a very small investment. And also we've made a quick payback time calculation and divided into percentage of uncertainty, because there is a lot of uncertainty in this study. And as you see, as we increase the uncertainty, the payback time is balanced between the rule-based and the AI-based control. And in an average, like 10% of uncertainty, you can see that in 4 years we can pay back the investment we've made if we deploy the rule-based control algorithm, and in 2 years if we deploy into the building the more advanced control algorithm. And my final slide is a discussion about this study, the benefits. As you saw, we have a proof that there is a benefit to switch to a more advanced control, as we can optimize on the same time comfort and energy performance. As we discussed in the previous presentation, that these are contradicting one another, comfort and energy performance. So I see, like, because we've done partial like demonstration of this algorithm in the building, I see in the first results we have that there is more comfort improvement rather than energy at the moment in the real life demonstration. As you saw, the more advanced reinforcement learning outperforms the rule-based, and the estimated payback time depending on the energy uncertainties, because there is occupancy uncertainty, weather uncertainty, so it's not easy to estimate the energy savings. The issues now are that the advanced algorithm requires expert knowledge and a lot of time to fine-tune and set up to work in the building. At the moment, it's something we need to optimize. And it's way more complex than the simple rule-based. So in the future, we want to understand if it's really feasible to deploy in a building this such advanced algorithm, or just continue with the rule-based solution and try to optimize using similar case studies in the project. So we now, at the moment, we're testing the deployment of this algorithm in another building, in another case study we have. And that's pretty much me for today. And you can follow iBECOME in the social media, and you can navigate to the page to see more details. We publish our reports on our website if you want. We have a lot of public reports you can download with more details, and more are coming, so you can stay tuned. And that's me. Any questions? Coffee is waiting as well.
Which variables are you monitoring for the?
Sorry?
Which variables are you monitoring for the calibration of the energy model?
Yeah. So we do basically two types. Like, one is the energy calibration, the other one is for the environmental conditions. So if we want to calibrate for electricity, we monitor electricity meters. And it works better if we do sub-metering. We like to measure the lighting use, measure the plugs and all stuff. So it's better to do with many meters. And now for the comfort, like calibration, if I can say it like this, we use sensors like air temperature, humidity, CO2. And we do measure illuminance, but we don't yet calibrate for illuminance. So we focus primarily on thermal comfort, and then on air quality using CO2 as a proxy also for the occupancy. We do have motion sensor, and we combine the CO2 with motion sensor to also create a better profile for the use of the building. Okay, because in general, in energy modeling, we're using like template profiles. Like, office is like 9 to 5, but in reality, this room now will be empty for, let's say, 2 hours. Maybe in 2 hours there will be more people coming. So we try to capture these profiles into the modeling, because it plays a very important role in the energy results you get. The energy model.
I have a question regarding this thermal comfort, and you showed, I don't know which typology, building typology, because you showed a slide that the overheating was something like 23 degrees. That is overheating.
Yeah, right.
So,
Don't know if I can solve it.
yes.
The results you mean here.
Yeah,
This is the current situation. Like there is quite a lot of overheating in the building. Okay,
so
and
for
even
general
in winter,
comfort, you consider that indoor temperature is overheating?
the 22 to 26. Yeah, we consider this based on the study we've made, like a survey with the occupants, and we associated their responses with temperature at that time they gave us their feedback. Okay. So we asked them and we collect some data and we realized that in this temperature zone, they replied that they feel like that it's overheating and
Office building.
yeah. Okay. We're good. We're done.
Yes.
Okay. Thank you.